Okay, so here's question 4. Billy's kite has a string 40 meters long. Oh, it's actually that one's on the board. Who wanted question 4? That one's on board 7. You have a 40-meter long string, so that's going to be the hypotenuse of that triangle. It's flying 27 meters above his eye level, and so that's going to be that vertical side on the opposite of the angle in the bottom left-hand corner. And you want the angle of elevation. So angle of elevation and angle of depression are both measured from where you're looking straight across. Angle of elevation means you go across and up. Angle of depression means you go across and down. So that angle there that I've labeled with that symbol theta in the bottom left-hand corner is the angle that you're looking for. So you have the opposite side and you have the hypotenuse. So you're going to use sine because of SOHCAHTOA. So sine theta equals 27 over 40. You're going to take the inverse operation of the other side. So on your calculator, you use sine inverse of 27 over 40. If you do that, you should get 42 degrees. Yes, Brad.
I got 5. It's just I didn't like write it down. Like my calculation.
1 sec. That was 4.
Yeah, I know.
Hold on. Yeah. Okay.
You said you would go over 5 because I asked, and it's fine.
Oh, you don't want me to do 5?
I need to throw the calculation on like a different calculator, but I haven't written down the equation.
What calculator did you use? While you're digging that out, Dwayne, you wanted 4? Does that make sense? Okay. Did anyone else who had questions on 4, did that explanation kind of make sense? No one else needed 4? Okay. So Brad, you wanted 5.
No, I just got to do the calculation. Actually, we'll just see if I have the right calculation. I just didn't throw it into the last part.
Okay. So what it would look like at an airport driving down a ramp, it's 96 meters long, 13 meters below. So this is how you need to set it up. I'm not sure if this is how you set it up, but that's what it needs to look like. So that's 96. This should be 13. You know what? Maybe my answer is wrong. I don't think it is, but we're using sine again because it's opposite over hypotenuse. So it should be the sine inverse of 13 over 96. Should look like that. Whatever you're punching into your calculator. So if that's what you punched into your calculator, then you need to double check what mode you're in.
I was using like how we used it, how we did trick questions and pre-calc, like the thing where you have the 3 sets of like angles and sides, and one of them has like the angle on the side, and then it's this like big thing that I can overcomplicate it.
Sine law?
Yeah. I just overcomplicated it.
Okay. I can take a look at it if you want, but that's how you'd go about it. Okay. And then Kai wanted 7. Emma also wants 7. Here we go. Question 7. So the biggest issue with 7 that I saw was that it was improperly drawn on every board for the people who attempted it. Kai had it wrong on the front. There was a group of ladies working at the back. And you got to be really careful when they use language of angle of depression. So there's your taller building. Here's your shorter building. It's supposed to be square, but it's not. And it says the angle of depression from the top of the buildings, of the top of the Billings building from the roof of the Wolcott building. So this is a Wolcott building. This is your Billings building. And the angle of depression is 33.10 degrees. So what that means is this. This angle here is 33.10 degrees. And then it says from the 15th floor, it's 21.50. So you're here. I don't know, let's call that the 15th floor. And then you're looking across again and you go down. This angle here is 21.5. This is how it should be drawn. That angle, that language of angle of depression is this is what it means. This is why it was originally listed as a bonus question too. So if the distance between the roof and the 15th floor is 101 meters, so this is 101, which means this distance here is also 101. Question says, how far apart are the buildings? So, this is gross. We'll call this value here x. Here's how I would do this question. I would call this little gap here x. And the horizontal distance here we know is the same. So I'm going to call this guy y and this guy y. They are the same. So we're going to have two expressions here. One for the top triangle. Sorry? You're good? Okay. So we've got two right angle triangles. I'm going to use tan for both of these. We know that there's a side that they share. The side that I've labeled y is the same in both cases. It's the horizontal distance between the buildings. So that's the adjacent side. The opposite side, one of them is going to be x, and one of them is going to be 101 plus x. These two added together. And so what you're going to get is that the tan of 33.10 is going to equal opposite over adjacent. So it's going to be 101 plus x over y. And the other one is going to be tan 21.5 equals, let me make sure I'm on the screen here. Tan 21.5 equals x over y. Now, they share so I've set these two expressions up, one for each triangle, and there's a variable that they share that's equal to each, that it's the same on both sides. So what I'm going to do is I'm going to isolate each of these equations for that variable. You're going to get y equals 101 plus x over the tan of 33.10, and you're going to get y equals x over tan 21.5. I'm running out of space, so I'm going to go over here. Now, if both of these are equal to y, what it means is that both of these expressions are equal to each other. And so you're going to get this awful expression, well, sort of awful. You're going to get this awful-ish expression where you have 101 plus x over the tan of 33.1 is going to equal x over the tan of 21.5. And now this is the thing you have to solve. At this point, it's just algebra. This guy's going to multiply up. This guy's going to multiply up. This guy, do you want me to, Emma, do you want me to keep going? Do you want me to do the whole question? Or is this enough? Okay. That's what this thing's going to look like. Would anyone like to see the algebra? Okay, let's do it. So I'm going to multiply the 21.5 up on both sides. It's going to cancel over here. It's going to move up over here. I'm going to do the same thing with the tan of the 33.1. So we're going to get tan of 21.5, and you're going to get 101 plus x in brackets is going to equal tan of 33.1x. These are going to distribute in. This is just what it is. So this tan of 21.5 and this tan of 33.1 are both just some decimal value. I'm going to leave it the way it is as tan 21.5 because I don't want to introduce any rounding issues. It's going to make it look gross, but that's mathematically the best way to treat this thing. So I'm going to get 101 tan 21.5 plus x tan 21.5 equals x tan 33.1. I'm going to subtract this guy over, and so I'm going to get 101 tan 21.5 is going to equal x tan 33.1 minus x tan 21.5. These are all just, this is just a number. 101 tan 21.5 is just a number. Tan 33.1 is just a number. Tan 21.5 is just a number. It would be no different than having like 5x minus 2x is 3x. So at this point, I'm going to start punching things into my calculator. Tan of 33.1 minus the tan of 21.5. It's gross, but that's the value. So you're going to get 0.25798132231x is going to equal 101 tan 21.5. And then I just divide both sides by this value. So you're going to get 101 tan 21.5 divided by that number. Oh, shoot. Shoot, I screwed this thing up. Nope, I did not screw this thing up. We're going to get that x is equal to 154. I did not screw this up. 0.23 is the value for x. But you don't want x, you want y. So then once you have a value for x, you have to go back and plug it into one of these equations. So what I'm going to do is I'm going to take this value and I'm going to divide it by the tan of 21.5. Boom. And you're going to get that y is equal to 391.5. Take that value, plug it into that equation, you get that. There's a reason the question was originally listed as bonus and that I still wanted you guys to attempt it. This is, and again, for those of you who are concerned, this is way uglier than anything I would ask you to do on a test or a quiz. So if you're sitting here looking at saying, I could never do that, that's okay. Outside of practice for homework to see what you guys are playing with and capable of playing with, this is the absolute grossest thing I would ever ask you to do in class, and I would never ask for anything this bad on a test or a quiz. I don't know, Kai, did you get this value?
In my dreams.
In your dreams.
Yeah.
You did? Okay. So the short answer is yes, but not very many people. I had a couple people who pulled it off last semester too. It's an ugly question. It's not beyond, like, the math here, the skills that are required are not beyond anything you would have done in a pre-calculus or like a Foundations of Math 10 class. It just pulls in skills from trig, it pulls in skills from solving equations, it pulls in skills from some basic algebra, puts it all together and shakes it up, and it is ugly, but the individual skills aren't beyond anything you would have done individually in a Foundations 10 class. There's a lot going on. Yeah. There's a lot going on. And it's easy to get lost in the muck. But there's a reason why it was originally called bonus. There's a reason why it's the last question listed on a page. It's good to play with. It's good to try and stretch yourself. But again, I don't want anyone sitting here freaking out because this is the question you couldn't do. The first 5 questions are way more in line with what I would ask you to do. The first 5 were all the same kind of question. 6 got a little bit weird because if you look, like, so on the board where it says between 9 and 10, 6 was a little weird because, and again, it had you, there's an extra step where you have to think about what it means for a pendulum to swing. And so that line needed to be the same distance straight down. So you have another scenario where there's a variable you're introducing in 6, and then 7's a whole other animal. But just because it's harder than anything I would ask you to do doesn't mean it's not worth trying. Okay. Questions, comments, concerns? Okay, if there are none, now let's move on to something entirely different. Sig figs. Hands up if you have studied sig figs before. Hands up high. Where? Chemistry. Hands down if you learned them in chemistry. Hands still up if you learned them anywhere else. Where, Dwayne? Oh, you did them in math. Which class? Oh, back in middle school. Sorry, did you say math 8? Oh, math 10. Who's your teacher? Oh, okay, different school. Okay. Sig figs doesn't usually show up in math. That's interesting. Chemistry is the first place that most people are exposed to significant figures. And chemistry is absolutely the best place to see sig figs. Sig figs, or to extend it, this is significant. Am I recording? I am recording. Significant figures. Really what it's asking us to do, or what we're going to talk about here in significant figures, are which numbers do we have that are actually important values. And chemistry, sig figs are really, really important. Everything we do in chemistry is as close to real science as you're going to get in a high school situation. When you're doing stoichiometry, or when you're converting things, when you're mixing chemicals together and you're trying to produce a product, all of what you're measuring, all of what you're producing has real value. It has actual meaning. When you measure 700 mils of something in a lab, you're actually measuring 700 mils of something. Chemistry is the closest thing to real science you're going to do. In physics is a kind of a different animal. In physics, when we do a lot of what we do in class, there's all sorts of stuff that we're going to ignore. When we do projectiles, you're going to do a lab where we shoot some dart guns down the hallway, up into the air and then down the hallway. In that lab, we're going to ignore the fact that air exists. Because to consider the fact that air does exist makes just the fact that air exists makes the problem so mathematically difficult that we can't actually attempt it with the math skills you have at this level. So we ignore the air. We are going to do an activity with pulleys. We're going to hang something off a desk. We're going to have a string, and we're going to ignore the fact that the string has mass. Because as soon as you acknowledge the mass of the string, the math becomes so difficult. I've only done it once. I have a master's in math. I wasn't allowed to consider that strings had mass until my master's degree. Because the math gets so ridiculous so quickly that we just couldn't attempt it otherwise. So we're going to ignore the fact that the ropes have mass. We're going to ignore the fact that the air exists. We're going to assume that everything's a sphere because it's easier. And so because we ignore so many of those things, so much of what we do in this class is going to be approximation anyway, that really to have a meaningful conversation about sig figs is, that's really almost impossible to see when I do that. To have a meaningful conversation about sig figs is hard to do in physics because so much of what we do we have to ignore anyway. That said, sig figs have a pretty significant, pardon the pun. Sig figs have an important place in physics when you're doing labs. So for those of you who are going to go off and study physics or study engineering, sig figs are really quite important. And so we touched on them here a little bit as well. Sorry? Okay. So I know you've done it all already, but here's why it's important in physics. If you've done it in chemistry, that's great. Accuracy and precision, what's the difference? Before we get into physics, we're going to talk about, before we get into sig figs, let's talk about this. What is accuracy? What does it mean to be accurate? Yeah. How close you are to the target? Absolutely. Accuracy is, so in a lab situation, we're going to call that target the expected result. So accuracy is how close you are to an expected result. So an expected result in the lab setting, an expected result is the value I tell you something is. I mean, we have got the targets up here because this is when we typically think about accuracy and precision. And a common thing to think about is shooting at something. So I've got my archery set up here. If I had to draw accurate, you might draw it like this. If this is how, if you go to the archery range or you go to the shooting range, and if this is how you're shooting, we would say that you're pretty accurate. Your shots are all around that center bullseye. If that's accurate, what does it mean to be precise? Hitting the same spot again and again and again. So precision or preciseness is how consistently you get the same result. So this might be accurate, but is it overly precise? Not really. I mean, you're close to the bullseye in every single case, but what would precision look like if not accurate? Precision might look like this. You might get a really close grouping. This is precise. It's not accurate, but it's precise. This is accurate. You're close to the expected value, but you aren't precise. You're kind of all over the target. Which of these is better? Do you think? Anyway, in the lab, on the gun range, archery, which of these is more advantageous? What do you think? Why do you think accuracy is better?
Doesn't matter if it's precise if you want to be near where you want to go.
You want to be near where you want to go. Does anyone disagree? Which of these is easier to teach? Is it, so let's say you're shooting something, archery or gun range. Is it easier to teach someone to be accurate or like to tell them where the target is? Or is it easier to teach someone to be precise? Teaching precision is easier? I mean, teaching accuracy is as simple as leaning over and saying, you want to get it in the middle. It can be. Which of these is harder to attain? Is it harder to be precise, to get your shot in the same spot every time? Or is it harder to find, like, to know where the target is? It's harder to be precise. For those of you who have never been out shooting, it's a hard question to answer. But even if you've been shooting 10 minutes on the gun range, you'll learn really, really quickly. This is a lot harder to do. This is more difficult. If you're at the gun range,
I heard gun range.
you heard gun range?
I'm in.
If you're at the gun range and this is what you're doing, if all your shots are here, what's the problem? But why aren't you hitting the target? If your shots are like this, is this a you problem or is this an equipment problem? If you're shooting with this level of precision, is that an equipment problem? Or is that a you problem? Mr. DeVries, is this a you problem or an equipment problem? This is an equipment problem. What's the problem here? Mr. DeVries.
Oh, the scope's off.
The scope's off.
Yeah.
So this is
Not accurate all the time. That's a
oh, precise is the language we're using here. This is what we call systematic error. There's a problem with if this is how you're shooting, there's a problem with your equipment. So if you're on the gun range, your scope's off. That's easy to fix. Your scope it's a couple clicks on one knob, it's a couple clicks on another knob, and all of a sudden you can drag your shots over by tweaking your equipment, and now every single shot is dead center. Just a little bit of anecdote. This is how I shoot. My shots are spread. This is how my wife shoots. To sight. It's a lot harder for me to get my gun to the point where it needs to be because I'm not as precise a shooter as my wife is. My wife took 3 shots, put them right there. We tweaked the scope so it was over, and this is what the next 3 shots looked like this. The first time I took her shooting, she put 3 bullets through the same hole. My wife is a phenomenal shot. I am not. This is what you want to be. You can be accurate and precise. Precision is more important. Precision means it doesn't matter how many times I take the measurement, I get the exact same value. Even if that answer is wrong every single time, then it's not a you problem. Then it's an equipment problem. You can go back and you can tweak your equipment. This is what it looks like to be precise and accurate. Obviously, this is the goal. We want to be accurate, but precision is the thing we want to get first. Taking measurements of things the physics lab isn't going to be nearly as fun as going to the archery range or going to the shooting range, but the concepts are the same. You want to, as much as you can, make it your goal to be precise with what you do. And then if you find that what you have found is off, then there's another reason for it outside yourself. So here's what we're going to do. This is kind of where sig figs come into play. I am going to give you, I'll give it to, say you and a partner, or if you're at a desk with an odd number of people, you and the people sitting at your desk. I'm going to give you guys some measuring devices. And I want you to do some measuring for me. I would like you guys to measure the length and width of your desks. How many of these do I have? How many of you are 5, 6, 7? You know what? You're each doing your own. I don't want you working with anybody. You know that one. You know that one. Okay, you can toss that there. I want if you can have this guy. Okay. 1, 2, 3.
Wait, you wanted the length down the middle?
Length and width of your desk. No, just top, the flat part at the top. Length and width. Not depth. Length and width.
Freaked me out. I stopped.
You gave the
There you go. Everyone needs a measuring utensil. Let me know what you got when you. I have some writing to do. Okay, so we've got at this table. I've got Lachlan, Kale, Kai, and centimeters. I want everything in centimeters. Centimeters. And Marcus. At that table, I've got Kaylin, Brad, Arlene, and Ray Reed. Don't discuss with the people you're sitting with. Get the values on your own. Back, I've got Henry. I've got Dwayne. I've got over there. I've got Janaza. I've got Jack. I've got Sire. I've got Ezra. Colden's away. You got to do in centimeters. William. And then on the middle table, I've got Emma. I've got Irem. I've got Julie, and I've got Vicky. Alana. Once you've got two values per channel, I'll come report it from you.
Yeah, wait, how are you getting that?
What is wrong with you? No, that's not right.
This is 30. That's 30.5. I did for
Okay, gentlemen.
Wow, you want to do 0.7? I'll get 7.5. Oh, here, let me get him running back. 7. 30. 60. We don't round in these things. You know, let's say you're wrestling guy. Let's say you're wrestling guy with like 2.1 pounds of cocaine. You round down to.
Yeah, you just take it for yourself.
Exactly. Can't do that.
Yeah.
Whenever there's like a shampoo,
Yeah, right now, yeah. Oh, I got 50 on the top.
You didn't.
Yeah, I did.
It's not 50 on the bottom.
Oh, I got.
Is that 20 on the top?
Yeah.
This guy's 12. The long way is 75.7. So
systematic error.
Long dimension, short dimension. And I did 15 centimeters.
Exactly.
Yeah.
At least you can actually read yours. Oh, you know what? I kind of think it's 15. So I rock climb with some like exchange student every time. Where do you go? Every time I get climb.
Lachlan.
Stop. Where do you go? Stop.
What'd you get?
Where's that?
Kale, what'd you get?
75.6. And 5.7.
Okay, so I gave you guys all sorts of different tools to use, and these are the values you got. Lots of you were certainly in the same ballpark. One of you I gave a wildly subpar measuring tool to. Sire, would you hold up the ruler I gave you? That's the entire ruler. How many centimeters long is it? It's a 15 centimeter ruler. Lovely. And some of you guys got a full-on meter stick, which was largely in excess of what you needed. My value for this, I did this measurement as well. My measurement for this was, and again, I'm not saying I'm not giving you this measurement to say that I am the arbiter of truth in all of this, but I did the same measurement you guys did, and I got 75.8 by 50.4 is what I got when I did this measurement. So lots of you guys were close to each other's values. We have 75.8 by 50. So it seems like if we were to look at this, the consensus would seem to be that we got somewhere in the neighborhood of 75.5 to 77. So if we average that out, we got 76-ish by 50-ish. There was values between 49.9. We had a 41 down here. That's an interesting value. We had the value with the wildly subpar tool. And then we had, but otherwise we seem pretty close. Now, some of you guys gave me values that were different levels of precision. Over here I've got, and I'm using precision differently here. This one, Sire, you said 49.75. So this was a centimeter. You guys all had centimeters on your rulers. Some of you had millimeters as well. Some of you did not have millimeters. The hands up if your measuring utensil had millimeters. Maybe I'll do this the other way. Hands up if you did not have millimeters on yours. Kai, what did you use? There's no millimeters on that thing? There's millimeters on that thing. The little lines in between are the millimeters. These are millimeters.
I've never measured by millimeters before.
Some of you guys got really blurry rulers that look like this, where some of the lines were almost impossible to see. The white meter sticks, I don't know if they do. Oh, they totally did. But the white meter sticks I gave you, some of them were busted on either end. But largely, these seem pretty good. Not all of you were exactly the same, so the question is, how close is close enough? If we start to look at these values, what would we say is, are there any that you would rule out as being not close enough? What does your gut tell you? Which ones? We don't like Ezra's values. Ezra would say that Ezra wasn't close enough. Well, who knows? You don't know what tools I gave him. Look at Ezra's ruler. Ezra got a different ruler than the rest of you guys got. If you take a look at the values that are the most out, Sire's and Ezra's values, they have radically different measuring devices than the rest of you. Ezra got the bendy rubber ruler. Sire got the ruler that's way too short. That was just the luck of the draw. And those were the values that we would say aren't close enough. But the rest of you guys didn't get the same values either. If you look at Harlene's values, we all got 75.8. She said she was around 75.5. Harlene threw down a 77. Is that close enough?
No.
Why not?
I don't like that number.
Why don't we like that number? What's wrong with that number?
I'd say it's more than centimeter off.
It's more anything that's bigger than a centimeter off what though? The average, my measured value? What's the standard here? The average?
But the average, you can't say that. The average is all.
I mean, if we averaged all your guys' values for for a particular dimension, is that a reasonable way to kind of find the accepted value? Could work. Are there any other values that you would want to toss? The 70, you don't like the 76.5? It's 76.5 is closer than 77. Who's to say that this is too far out? And so, I mean, really, some of this is just going on your gut. You're like, I don't like that 76.5. I don't like that 77, but you don't really necessarily have a good reason why. In the lab, we have rules for what makes something close enough or not. When you guys should you guys go on and study physics? First year physics in the university, or you start doing, or engineering, if that's the path that you want to take, there is a whole world called error propagation. Before we finish this, how close is close enough? Let's talk about error. You guys have a whole bunch of different values here. Error isn't necessarily about how right or how wrong you are. Error is built into everything. You can't necessarily be 100% correct because someone made the rulers that you guys are using. For some of you, someone rubbed out the values that you were trying to use. There's error. Anytime a human is involved in constructing a measuring device, there's error there. Because you can't assume that person's perfect. Even if they built a machine, someone programmed the machine. Someone constructed the thing that's constructing the thing that you're using to measure. Everywhere along the line, there are places where error can show up. So if for a measuring device, for a ruler, for a thermometer, for a scale, whatever the device is for measuring whatever, a stopwatch, a measuring instrument generally has a precision of plus or minus half the smallest division. And so what that means is if you were using a millimeter ruler, like if whatever measuring device you had, if it had a millimeters on it, labeled, what that means is plus or minus half a millimeter in your guys' case. So in what we were doing here, it would be plus or minus 0.5 millimeters. So what that would convert to, because all of you guys gave me your values in centimeters, what that converts to is plus or minus 0.05 centimeters. And so what this means is actually when you guys are doing these measurements, all of you could have reasonably quoted to 2 decimal places. Sire and Chinaza were the only ones that did. This is entirely reasonable. Some of you guys may have had, like, depending on how they're labeled, 2 millimeters was the division. If 2 millimeters was the division, then half of that would be 1 millimeter. Some of you might only have been able to go to 1 millimeter. Does any of you have that on your measuring device? None of you, every one of you had millimeters? Okay. But you yourself are also a source of error. And this is where Sire, unfortunately, this is where this came out. How did you measure your desk with a tool that was like way too short? Okay. Did you do anything to ensure that your ruler was level the entire way across? How'd you do it? Okay, your thumb was used as a triangle. Okay, cool. But Sire was at a disadvantage compared to anyone who had a ruler like a meter stick. You guys with the meter sticks, how did you determine that your meter stick was level all the way across your desk? You kept it square to the edge. Okay, but you can see how that would be a lot. Can you see how that would be a lot easier to do with a longer measuring stick than Sire had? Like, I think that's obvious to a lot of people. But so you yourself are also a source of error. How you choose to measure is gonna, like, the choices you make are gonna introduce error. Your biology is a source of error. Coming back to the shooting example, if you look at my hand, I've got a slight tremor. As much as I try and hold my hand still, let me see if you can see it, if it picks it up on the camera. This is me attempting to hold my hand still. You can see it's kind of bouncing all over the place. So when I'm shooting, the fact that I'm bouncing all over the place impacts my shot downrange. You ask my wife to hold her hand still, and it's still. Compared to me, it's not. That doesn't move. And so there's an error. Well, not an error, but my biology creates a source of error. I want you guys all to pull out your phones. I want you to pull out your stopwatches. And I want you to push, so open up your stopwatch, and I want you to hit start and stop as fast as you can. What do we get? What are some values out? This was mine. What do you guys get? 0.11, 0.11, 0.11, 0.06, wow, 0.13. What else do we got? 0.11. Harleen, what'd you get? 0.19. 0.08, nice. And so your reaction time is going to be another one. Just the speed at which your reaction to hearing a stimuli and then reacting to measure it. Someone right now is doing a biology IA on reaction time. Did anyone partake in that study? None of you guys did that? She was going, I can't remember who it was. She asked me to do it, to test reaction time. This is inherent in your biology, and the younger you get, not the younger you get, you can't get younger. The younger you are, generally speaking, the quicker your reaction time is going to be. They tested grade 9s, they tested grade 11s, they tested grade 12s, they tested staff members. Mr. Easton beat me. Actually, a PE teacher beat me too. I beat Mr. Whitman. I would hope I would beat Mr. Whitman. He's old. But your biology is another thing that introduces error. So an example here, reaction time. So when you guys are doing labs, when you guys are taking measurements, all of this stuff needs to be taken into account. When you go ahead and you actually do these things in university, there are calculations. There's calculus behind how the error gets calculated. For you guys at this stage, Physics 11, none of you have taken calculus yet. What we say to encompass all of these things, what we say is for you guys, close enough is going to be plus or minus 10% of the expected value. And so if we assume, so this is the value we throw down as a general rule when there is, without doing a proper error propagation. So if we assume that my measurements are the true measurements. I'm not saying that that's true. If we assume that, then if I take 75.8 and I multiply that by 10%, so 0.1, that's 7.6 centimeters. What this means is, if I'm plus or minus 10% of the expected value, that means every value between 83 centimeters and 68 centimeters is close enough. So on the low end, 68.2. On the high end, it's 86. Was it 86? I can't remember if it was 86. So 68.2 to 75.8 plus 7.6. Sorry, that's 83.4. Any long measurement between here and here is still technically acceptable. So Ezra, you're good. That's 73 we like. Sire, unfortunately, you're out of plus or minus 10%. But again, that was to be, whoever got the short one was to be expected. On these ones, the 50.4, that's going to be plus or minus 10% is 5. So anything between 45 and 55. If we go with plus or minus 10%, anything in this range is good. So all of a sudden, that value is good. And Ezra, that value's out. So we like Ezra's width measurement. We don't like Ezra's width measurement. But every single one of you, all the rest of you, got close enough. And actually, close enough is a pretty wide margin. Lots of you would look at 83 and say, well, that's ridiculous. But without proper error propagation, this is what we look at. So sig figs are a way to address this kind of problem. For you guys, as we're doing these things, all recorded data is considered significant. When you're taking a measurement, everything there is significant. However, the last digit is deemed to be uncertain, because that's where error starts to show up, is in that last digit. When you guys are doing calculations with data that you don't measure, so this is for non-measured data, data that's handed to you, these are the rules for sig figs. So here they are. If you've done them in chemistry, you've got a leg up on this. If this is brand new to you, here you go. All non-zero numbers are considered significant. So if I had 321, if that's the value I'm handing to you, there's no zeros here. This has 3 sig figs. Every single one of those digits is significant. If I gave you this number, 320, that 0 at the end of the value is not significant. We would say that this thing has 2 sig figs. Zeros that occur in the middle of a number are significant. So if you have, we said, even though that these are zeros, if you have a 0 between 2 sig figs, those zeros are significant. So this thing has 4 sig figs. These zeros become significant because the significant figures on the ends exist. In a non-decimal number, zeros at the end are not significant. So we said this before when I mentioned it up here. If there's no decimals, these 2 zeros are not significant. That thing only has 2 sig figs. If you have a decimal, zeros to the left are not significant. So this thing only has 2 sig figs. And in a decimal number, zeros to the right are considered significant. So this guy here would have 4 sig figs. So there's something I want to mention here too. This thing, we said in non-decimal numbers, zeros at the end are not significant. So if this was 5,200, 2 sig figs. As soon as I toss a decimal in there, if this was 5,000.0, how many sig figs would this thing have? It says in a decimal number, zeros to the right are significant. So this 0 would count as a significant figure. If this guy's significant, what does that tell you about these two? Zeros between sig figs are significant. Adding a decimal and a 0, even though these two values are exactly the same. 5,200, 5,200.0. This one has 2 sig figs, this one has 5 sig figs. Even though these two values are exactly the same. So, take a look at this top row here. How many, based on those 5 rules, and if you need to refer back to them by all means, how many sig figs are in this value right here? There's 2. How many here? Remember, zeros between sig figs are significant. So this one would have 4. This one here, 2. This one here, this one would only be 2, because these zeros to the left are not considered significant. The zeros on the left are not significant, zeros to the right are. So this guy would have, there's no decimal here, so this guy would only have 1. This guy would have 3. This guy here, also 3. And this guy here would have 6, absolutely. Based on those sig fig rules. Now, multiplying, dividing, adding, and subtracting change the resulting answer's significant figures. For example, if I just took in my calculator, I said, oh, I have 250, I'm going to multiply that by 1.15. So 250 times 1.15 is 287.5. How many sig figs are in this number here? 2. How many sig figs are in this? I'll put a little 2 up here. How many sig figs are in this one? 3. So this number has 2 significant figures. This one has 3 significant figures. This answer has how many significant figures? 4. We can't say that our answer somehow developed more significant figures than the numbers that went into getting it. So here's the rule for multiplication. The rule for multiplication and division. When multiplying or dividing numbers, the final answer is always rounded to least sig figs. So the least number of sig figs for the value that went in to get this is what? 2. So what we would do is we would take this and we would round 287.5 to how many sig figs? Where would we round this number to give us 2 sig figs? I'll say it that way. 290. 287.5 would round to 290, and now this thing has 2 sig figs. And that, in sig fig math, would be an acceptable value. This guy, if I multiplied these guys together, I would get 0.2695. How many sig figs are in the first value? Yeah, someone said 4. How many sig figs are in 100? Please don't bend the meter sticks around your body. I spent lots of time trying to straighten those out. There's only 1 sig fig here. So 0.2695 would have to be rounded to what? Yeah, this would have to be rounded to 0.3 to take into account the proper number of sig figs. This guy here on the left has how many sig figs? That decimal there with the 0, though, adds some sig figs. This decimal makes that 0 after it significant. So there'd be 4 here. And how many sig figs are going to be in 150? 2. If I multiply those together, I get 30,000. So how many sig figs does 30,000 have? It's only got 1 sig fig. So that's a problem. I need to quote my answer to the least number of sig figs. So how could I take 30,000 and create a significant figure for it? Yeah, add a decimal. But if I add a 0.0 at the end, now I'm going to get 6 sig figs. I only want 2. So I need to bring the decimals, but that's the right way to do it. I need to bring in a decimal, but now I need to have some way of moving it to the left, Kale just said. What have I already taught you is a way we could bring the 0 to the left. Scientific notation. So what we're going to do is we're going to bring this thing over 1, 2, 3, 4 times. It's going to take 30,000, and it's going to take it to 3.0 times 10 to the, it jumped 4 times. And now this value has 2 sig figs. So scientific notation isn't just about giving us nice numbers to work with. It's also about creating the correct number of sig figs in your results. So with multiplying or dividing, you want to round to the least number of sig figs. Adding or subtracting is a lot easier. Adding or subtracting, your final answer is always rounded to the least number of decimals. Adding or subtracting is a lot nicer. For example, this first one, if I added 25 and 57.65 together, I would get 82.65. But based on this adding and subtracting rule, this thing should actually be rounded to what? 83. This one had no decimals. This one had 2 decimals. So this thing needs to be rounded so that there are no decimals. That's addition and subtraction, a lot easier. This last one here, 0.6851 minus 0.337. If you punch that into your calculator, do it longhand, you're going to get 0.3481. What should this thing be rounded to? Yeah, 0.348, based on the rule for adding and subtracting. A little broke. So now, this unit is the only one that I am going to harp on you guys for sig figs. I'm going to give you a test. I'm going to assess you on your working with sig figs. Moving forward, all of the questions I give you for homework will have their answers to the correct number of sig figs. And what this is going to do is it's going to give you something to round towards. Because lots of you guys are going to introduce rounding errors. You do the questions that I assign you. As long as your value to the correct number of sig figs matches what's on the page, you're good, even if there's some wiggle room there. So I want you guys to say there's perfect timing. There's 4 minutes left. This, you guys can use a calculator for it, but you got to use the sig fig rules. This is your homework, and honestly, you can get most of it done in the time that you've got left. So use this time. I will come around. I want my measuring utensils back. I take a look at these sig fig questions, and when the bell goes, then you may pack up, unless you're done already. When the bell goes, you may also go. Have a great day. We'll see you later.